Hi guys, welcome to my talk today on time series processing with Solr and Spark. My name is Josef and I'm with QAware. It's a German custom software development company based in Munich. That's a very important information you'll see. We'll use this later on. The first slides are dedicated to our first-class citizens, the time series. Yeah, we want to perform time series analysis. And fact is that a lot of data is best represented as time series. Like operational data, we'll see a lot of examples here today, how to analyze monitoring data, performance metrics, log events. They're all time-bound, and they're all good represented as time series. Also in data warehousing, the dominant dimension is often time, yeah? And also this Internet of Thingy stuff, like measured me or sensor telemetry, also produces a lot of time-bound data, which is best represented as time series. And you can also see here, with time series data, you can also produce fancy visualizations of climate data. But as I'm from Munich, there is a very important other type of time series data for us, and it's a time series of the Oktoberfest KPIs. Yeah, you know? We collect it each and every year, and this is a chart of visitors in millions and the beer consumption in millions of liters. And by analyzing this time series, we were able to figure out a very historic moment in 2003. We call it the singularity, or also the Bavarian break-even, where from this point starting, each and every visitor at the Oktoberfest drank at least 1 liter of beer. So you can see time series data and analyzing time series is a very important facility. So let's clear some basic terms on time series. We distinguish between univariate and multivariate time series here. Univariate time series, it's the most easiest form. It maps timestamps onto values. And multivariate time series maps one timestamp to multiple values. This pair of timestamp and value is named an observation. It's at a certain point in time, the value we have. There is also the concept of multidimensional time series or time series tensor, where you assign a time series to a multidimensional space. If you're doing monitoring or so, you want to measure your metrics and you want to assign those metrics onto other dimensions like the host, where you've measured it, the process, where you've measured it, the geographical distribution, where you've measured it, and so on. And last but not least, there's a concept of time series sets. Basically it's a set of time series, a group of time series, where time series which are belonging somehow together are grouped together. We'll use some of those terms later on. Yeah, and when you have your glorious time series, you can do some operations on these time series. Basically, we distinguish between time series operation, which have a time series as input and time series as output, like aligning time series at a certain point of time, diffing the values of time series, doing downsampling, reducing the amount of observations, basically, and outlier detection, where you reduce a time series only to the points in time and the values which are considered as outliers according to some statistics. And the other part, the other type of operation is where you map a time series onto a scalar value, like the basic statistics, min, max, average, median. Also very handy in certain analysis is to calculate the slope of a time series, or to do more advanced statistics like standard deviation or so. Just to give you a few examples what you can do with time series. Our use case we faced was we needed to perform monitoring data analysis of a business-critical, worldwide distributed application. It's distributed on a little bit more than 1,000 nodes worldwide. There are 10 processes per node at least running, and we're collecting 20 metrics per process on various layers like operation system, JVM, or application-specific measurements. And all this is measured every second, yeah? So that we can perform root cause analysis, so that we can perform anomaly detection. If you multiply this, this leads to 6.3 trillion observations per year, and we wanted to have a data retention of 5 years. So this is really a huge amount of data, yeah? Trillions of observations we have to handle. What are we doing with those time series data? Here is a screenshot of a tool we wrote. It's called Chronix Analytics. And as you can see here, here is a region where you can drill down into the time series based on the dimensions they're assigned to, like host, process, measurements, and counters, the metrics. You have a search facility here where you can query time series based on their metadata. And the central part of the UI is this chart here, where you can superimpose time series to detect and correlate time series. If there is a performance problem in the United States, maybe the root cause is a failing database anywhere in the world, so you can superimpose those performance metrics with loads of database systems, load metrics of database systems. Yeah? This is an exploring facility here. Another thing we wanted to do is to do some statistics like box plot analysis here. This is especially helpful when you're doing sizing, to determine what's the memory consumption of an application or so. And we also wanted to perform automatic anomaly detection. We're using Twitter anomaly detection. It's open source at GitHub, and Yahoo eGADS. It's also at GitHub open sourced. And if you apply those anomaly detection algorithms on time series data, you're able to highlight regions like depicted here, where is probably some anomaly in the dynamic behavior of an application. Yeah? That helps to figure out where the pain is. Yeah, and last but not least, we're using Zeppelin, the Zeppelin notebooks, to create analysis stories. Yeah? You have your symptoms of some kind of anomaly in your system, and you want to document the steps until you determine what's the root cause. And for this purpose, we use Zeppelin notebooks, where we basically describe SQL statements against time series databases, or time series data, and we have our charts here. Yeah? That's our use case. So now let's get into the tool, the technology we've built to process this amount of time series data and to enable us to do our use cases. We called it Chronix Spark, or Chronix. Yeah? Chronix is a whole stack. Chronix Spark is one part of it. It's open source, and you can grab it from GitHub. Here's the URL. Yeah, as you can remember, we're facing trillions of observations. This is a clear big data use case. Yeah? We have to create a technology which is able to scale out. Yeah? We were not able to handle this data on one single box, even if we scale up. We need a solution which scales out. And there are some time series databases out there available. This is our big data landscape. We release it twice a year. And there is this region here with time series databases. The most famous ones are InfluxDB, OpenTSDB, and Kairos, and also Chronix, our solution, is part of this region of time series databases. They're all open source. And we decided to build an own. We decided not to stitch to OpenTSDB or others. We created a new one, Chronix. The mission is to create an easy-to-use, big time series data storage and processing, and we wanted to have it on Spark. To combine it with machine learning on Spark, to combine it with SQL handling on Spark, and so on, to have a very robust facility to perform distributed processing. The design goals of our Chronix stack were we wanted to have a big time series database which scales out, which is storage efficient. We don't want it to waste hardware, hard drive space, and it should enable us to formulate and express interactive queries against those large amounts of time series data. One further principle is we wanted to create a time series database which does not need separate servers. We wanted to have it as drop-in onto existing Solr and Spark installations. So you don't have to launch a separate Chronix server, so you just have your Solr cloud cluster, you have your Spark cluster, you drop our plugin in, and everything works. And we wanted it to be integrated into the relevant open source ecosystem. And this is how it looks like right now. We have basically 3 building blocks. The lowest one is the collection building block, where we gather the metrics from the systems, our time series raw data. We have integrations to Logstash, FluentD, CollectD. Also, we can act as long-term storage for Prometheus. And we have our ingestion bridge. This is quite new. It's going to be released within the next weeks, but it's already on a branch where Chronix from the outside looks like an InfluxDB, Graphite, KairosDB, or OpenTSDB. We have implemented those protocols, and so we can ingest data from all sources which support one of those other time series databases. At its very core, Chronix has 3 layers. The basic layer is Chronix storage based on Lucene to store time series data. It's used within Solr, and we have our Solr cloud. It's called the Chronix server to store time series data and to have some basic retrieval. And Chronix Spark on top of this stack to perform distributed processing. All is backed by Chronix format. It's how we encode and decode time series data. More on this later on. And the user-facing side are the analytics frontends. We support Zeppelin, as you have seen on the screenshots. We have our own Chronix Analytics UI, and we also support Grafana for metrics dashboards. That's basically the Chronix stack. Today, I want to focus on Chronix Spark. Chronix Spark, at the very bottom is Solr Cloud. We use Solr Cloud for distributed data and data retrieval. We do all those sharding stuff of Solr Cloud. We're using the fast index-based queries of Solr. It's best performing and very close to the data. So we use this there, and we've implemented our efficient storage format within Solr. One layer above, there is Spark, getting the data from Solr. We use it for distributed processing, doing all those heavy lifting, distributed processing stuff. And yeah, we've implemented a few techniques for efficient integration of Solr into Spark. Yeah, you have to think about how to transfer data efficiently here. And as result processing, you can use any driver language Spark provides, like Java, Scala, R, or Python. That's a Chronix Spark stack. The underlying time series model is that we represent time series, or our model is a set of univariate, multidimensional, numeric time series. That's our time series model. A set because it's more flexible. Yeah, you can superimpose your different time series if they're within a set. And it's better to parallelize if you have a set as a basic abstraction because each and every time series, it's potential good unit of parallel processing. It's univariate because we didn't want the complexity of multivariate time series. Yeah, we were lazy here, and we have our set, so it's not that bad. It's multidimensional because we really need it for our use case, analyzing the monitoring data, but also we're using Chronix, or other persons are using Chronix for other use cases, and it figured out to be a good choice to have a multidimensional time series concept to perform slicing and dicing within your time series space. Yeah, and it's numeric right now because it's the most common use case to have numeric values within your time series, but we're planning to support other data types, especially for log analysis. Yeah? So we need, for log analysis, we need a string value type for our time series, but right now it's numeric. If you think about time series, you have also to think about what's the identity of a time series. How can you identify one single logical time series? And our concept of identity is that one time series is identified by the combination of its non-temporal dimensions. So no matter how much time span it has, it's identified by the other dimensional values, like in our case, the unit, the host, or the process. And the combination of all those non-temporal dimensions is the identity of a time series. So that's our underlying concept. So now let's head into our API, how to use Chronix Spark. The entry points of Chronix Spark in the API are the Chronix RDD and the Chronix Spark context. The Chronix RDD represents a set of time series. This is our model, and the distributed operations on this set. And the Chronix Spark context basically creates Chronix RDDs and speaks with a Chronix server, speaks with Solr. The data model is we have at our root the Chronix RDD. A Chronix RDD contains metric time series. It's a set of metric time series. And metric time series are containing metric observations. Yeah? No surprise here. We also support transformations from an RDD onto a data frame of metric observations and transformations of an RDD onto a data set of metric time series or metric observations. RDDs, data frames, and data sets are the basic APIs of Spark to perform distributed processing, and they have some distinctive properties. RDD is typed, it's medium optimized, it's very mature, but it supports NoSQL. A data frame, in contrast, is non-typed and provides SQL statements. You can run SQL statements on a data frame. And data sets are pretty close to RDDs, but they're better optimized, and they're better performing. They're also typed, but they got stable within the last versions of Spark, so they're not so mature right now. That's why we support them all. So this is the interface of Chronix RDD. It extends a Java RDD of metric time series. This is a set characteristic. It provides some basic statistical operations here, yeah, to min-max, slopes. You can filter the time series within the set of time series. Especially, these operations are useful to selecting or filtering out time series with certain dimensional values. Sorry. And this is the metric time series data type contained within the Chronix RDD. And here you have your methods to access all timestamps, access all numeric values, or stream out all observations. This is an option to do streaming here. And you can also access the dimensions or even set the dimensions of a metric time series here. This is our basic API. Now I want to show you how to code against our API, how code looks like if you want to use Chronix Spark. The first thing you have to do is to initialize a Chronix Spark context based on a Java Spark context. This is a Spark API here. Then you define a Solr query identifying the time series you want to load into the Chronix RDD. Here, we're selecting all time series bound to the dimension metric with this specific dimensional value here, heap memory usage. Then you initialize a Chronix RDD out of the Chronix Spark context. You have to pass the query, to pass where it finds the zookeeper of the Solr cloud. You have to identify the Solr collection. Here, this is the encoding and decoding facility. After that, you can call any operations on our Chronix RDD, like minimum, maximum, or mean over all time series contained in this Chronix RDD. One operation acts on all time series within the RDD. So you get the absolute minimum, maximum over all those time series within. Or if you want to perform SQL statements, you can transform the RDD to a data frame. And here you can do your statement. Select time, value, this is the observation, and the dimension, process, and metric. You can have a condition here. It's a condition where the dimension process is bound to Jenkins Cholokia, the Jenkins process we have monitored, and obviously order this by time. That's basically one sample code how to use the Chronix RDD. Now let's get into the internals of Chronix Spark. So API is quite simple. If you want to have more high-level operations, you can enhance the Chronix RDD. But today I want to focus on how it's implemented, which concepts we applied within Chronix Spark. First, let's have a look on Solr. As I mentioned before, we use it for data storage and data retrieval. Data sharding is used of Solr Cloud. I don't want to discuss this anymore because Solr Cloud provides it out of the box. Also, fast index-based queries, I think you all know that Solr is capable of doing so. No discussions anymore here. But the efficient storage format, it's interesting how we encode and decode time series data here. The basic idea is to perform chunking. We have our logical time series here, and we chunk this logical time series data into physical chunks of the overall time series. And such a chunk has its start and end timestamp, is bound to dimensions, and has the observations within. The observations are binary encoded here as a byte array. More on this later on. And this chunk is represented as one Solr document. We store one chunk in one Solr document. And those chunks are not time fixed. They're fixed in the amount of observations which are stored within this byte array. We don't do chunking by 5 minutes or so. We're doing chunking by amounts of observations we store within such a chunk. Yeah, and so one logical time series leads to several chunks, each stored in one Solr document. Yeah, and how do we do the encoding of those observations, those byte array representation? We're basically doing binary encoding of all timestamp value pairs, our observations. We're using protocol buffers by Google to do this. And we're applying binary compression on it, so the data gets compressed there. We'll also, before we do the binary encoding, we're doing a delta encoding to reduce the amount of data and to allow the binary compression to be more effective. Yeah, because time series data has sometimes only in terms of value, and also, as I will show you later, in terms of timestamps, has only a small delta. And if you can reduce this to null, it's very good for our compression algorithms. So we're doing delta encoding of timestamps. We call this DCC, date delta compaction. And we're also doing delta encoding of values. It's a normal diff. Yeah? We just store the diff between the values, two consecutive values, and it's good if the diff is null. Yeah? And it's often the case that in monitoring data or so, there is no delta between the values. But we're also doing delta compaction of timestamps, and the basic idea, and it's also published in a research paper, is that we have our chunk. It spans time, and it has a number of observations. And we calculate the periodic distributed timestamps. As you can see here in green, the intervals are the overall time span divided by the number of observations, and so you have your periodic timestamps. But normally, your observations are not periodic, so you have your real timestamps, and there are aberrations here between the real timestamps and the periodic timestamps. So what we're actually doing is we're calculating the data between the delta between the periodic timestamps and the according real timestamps. If this is within a threshold, we set the real timestamp to the periodic timestamp. If it's very, very close, we just set it to the periodic timestamp. And then the value we store is the delta between the periodic timestamp and the real timestamp. And in some cases, in a lot of cases, it's close to null. So we're able to reduce the amount of data here. We've tuned this. The question is which chunk size to use and which codec, compression codec to use. We've benchmarked it according to the storage demand and the access time of those chunks, and figure out that GZIP with 128 kilobytes of chunk size is performing best in terms of storage demand and access time. You can also read this in our paper here. And we performed benchmarks between this Chronix format and the formats used in other time series databases, most famous ones here. And in terms of storage efficiency, you can see here, we have ingested 108 gigabytes of raw data, and this leads to 8.7 gigabytes of data encoded with the Chronix format, and it performs best. Second best is InfluxDB here. This is also, you can find this in this paper here. Next is the performance benchmark. What's a performance of typical queries? And also with the other famous time series databases, we applied a query mix of very basic time series queries and high-level time series queries, which are very useful for our use case, monitoring data, like outlier detection, trend, or frequency analysis of time series data. And within this query mix, we're also performing best here. And the second best is, again, in FluxDB. So this is the Solr part. Now let's go to Spark, what we did there. We use it as distributed processing, doing all those heavy lifting things, and we focus on an efficient integration of Spark and Solr. So how do we achieve this? I brought some best practices with me. One best practice is to align parallelism between the Spark part and the Solr part. So what's the unit of parallelism in Spark? In Spark, the unit of parallelism is a partition. Tasks are applied on partitions, and each task is one unit of parallelism. And the unit of parallelism within Solr is a shard. So we align those parallelism in terms of we assign one Spark partition onto one Solr shard. Yeah, and in a Solr shard, there are several Solr documents representing our chunks. And at the Spark side, we have our partition containing several time series, and those time series are materialized from those Solr documents and chunks here. Okay, thanks. You have to ensure that a logical time series or the according chunks are located within one Solr shard and not distributed between Solr shards. Otherwise, you have shuffling. Yeah, this is how this looks like in code. We're using a cloud Solr client to get the number of shards for our collection. And within Spark, this is Spark code here, we parallelize on those shards and doing the deserialization of the chunks here. Yeah. Another best practice is push down. Delegate work from Spark to Solr, as Solr is closer to the data. And we're doing predicate pushdown. In terms of pre-filtered time series we're using in our Chronix RDDs based on their metadata. Yeah, queries on dimensions, start and end points are delegated from Spark to Solr. And we're also doing aggregation pushdown. We perform pre-aggregations at ingestion time into Solr, where we store default aggregations like min, max, or average, and we store them as metadata associated to our chunks. Yeah? And so we have pre-aggregated values within our chunks. We're also working on to perform aggregations on query time, but for this we have to enhance Solr a little bit more, that it's able to decode those observation byte streams. Yeah? We didn't do this right now, but we're working on it. And this is how it looks like. You've seen this code before. We have our Solr query, and we use and we express our filters within this Solr query. You've seen this metric dimension filter before, and you can also formulate some aggregations here within. And this Solr query is stitched into the Chronix RDD, and the Chronix RDD only gets access to this data pre-filtered by Solr. So we did our push down here. So last principle is efficient data transfer. We have our Solr here and we have our Spark here, and it's important to transfer the data from Solr to Spark in an efficient manner. An important concept here is to reduce volume. Yeah? It's a very good thing to try to reduce the amount of data you have to transfer. The mechanisms here are pushdown, as you've seen before, and compression, as you also have seen before. We decompress the data within Spark, not within Solr. and using efficient protocols with low overhead, which are able to do bulk loading and which are also able to do streaming within Spark. And this is our architecture here. We're using the Solr Cloud or the Solr export handler, which is able to bulk transfer results of Solr in the format of JSON tuples into a cloud Solr stream on the client side, on the Spark side. And so we have our stream of documents transferred via bulk, and we apply the format decoder within Spark, and then we get access to this data within the Chronix RDD. And the red ones are Solr J classes, and the blue ones are Chronix Spark classes. The last principle here is to avoid remote transfer. So this is to achieve it that this isn't a remote way here. The principle is data locality. We can try to put Spark agents on the Solr nodes and to achieve that the Spark tasks are on the Solr node where the shard resides. So you can perform your logic on the node where the data is. We don't do this right now, but we plan to use Solr RDD as soon as it supports Spark 2.0. There's already a branch of Solr RDD supporting Spark 2.0, but as soon as it gets general available, we'll use Solr RDD for this. More on efficient data transfer in this talk of my colleague Johannes Weigand yesterday, leveraging the power of Solr with Spark. Maybe you can grab his slides. There is way more information on this slide deck than in my slide deck. So let's flip over this code. This is how this is coded. Yeah, the slide's going to be published, so don't need to photo it. But let me conclude right now as time goes out. One point is that, in my opinion, time series databases should be first-class citizens. Hope you grasp it a little bit, how many different kinds of data are best represented as time series. And so I think time series databases are a good kind and a first-class citizen of the database ecosystem. And Chronix is one of those time series databases, and we leverage Solr and Spark to achieve two things: storage efficiency. Yeah, we've benchmarked this. We're best in class, I think, in this term, and to allow interactive queries for big time series data. If you have a huge amount of time series data, we can achieve to have interactive queries with our tooling, as I've showed you. Yeah, that's all. Thank you. Any questions? Yeah.
You're saying that the optimal performance is achieved when you actually push down. So why
Yeah.
can't we do everything in Solr itself? Why do we need to do a distributed layer in Spark?
The question is, if I mentioned that the best practice is to do push down, why don't we do the processing within Spark, right? Or
Why do we need to do it in Spark? Can't just Solr
do everything in Solr. Yeah, excellent question. We can do everything within Solr, but figure out for us if you have really, really huge amounts of data. Spark is the better way to go, as its distributed data processing is a little bit more mature than Solr, especially if you want to apply high-level algorithms like in Spark ML. if you do machine learning, and there are also a lot of other algorithms available within Spark. Yes. The question is, what's our query performance if... Pardon? The question is, what's the query performance if we query a time frame of 1 month or more, and what's the overhead for those data processing there. The query performance, if we have some queries, we applied some queries over a couple of years, and this query finishes within few seconds or so. Yeah, we're always below 1 minute. That's a weak point. The ingestion process right now is not very tuned because we didn't need this. Yeah? We have daily observations, daily monitoring data, and it gets ingested within few hours or so, or yeah, not few hours, about an hour. And but we didn't focus on having a low ingestion time. But at this talk of my colleague, Johannes Weigand, is over there, he presented some approaches how you can parallelize the ingestion process into Solr Cloud within Spark. But we didn't apply this right now on Chronix Spark. The overhead is pretty low because it's also in parallel. I didn't measure it, sorry, but it's supposed to be, don't know, low percentage degree of the overall processing time because it's parallelized.
And you will save the time because you are encoding and the amount of data is very low, right? So you will save
yeah.
reading the data also. Because you're storing deltas and you're doing encoding, do you expect the time always to be monotonically increasing?
Yeah. Yeah.
Because if you're collecting from, as you said, 1,000 nodes, multiple servers, there's no guarantee that the time coming to your Solr server will come in monotonically increasing time. Is that why you're doing batching?
Yeah. We delegate this problem into the ingestion process. The ingestion process has to handle this if there is a late event or so. Yeah. We don't handle this within Chronix. We assume it's monotonic. Yeah. Stop. Okay. If there are any more questions, I'm up there or anywhere around. Thanks.